The techniques that we've learned about with the sampling error of the mean also apply to proportions. So while we can take a sample and use that to learn about a population, in means, we can do the same thing using proportions. And it works a little bit like this. We have a population of an unknown proportion. In the example that we're going to use, we're going to take our ICU data, the proportion of the patients who died, which is the variable called expired, and we will use that population proportion and we'll compare it when we draw a sample. We have a population of an unknown proportion, and from that population we draw a simple random sample. That simple random sample is going to give us a proportion, which we call P bar, and we can use that sample proportion to infer that the population proportion is the same. If our sample has a proportion of 0.47, then we will infer that the population also has a proportion of 0.47. Well, how are we able to do that? We are able to do this because the sampling distribution of the proportion is this probability distribution of all of the possible values of the sample proportion, which is the P bar. As long as our sample is large enough, then the sampling distribution will approach a normal curve, allowing us to use a normal curve in the same way that we did for the standard error of the mean. The sampling distribution of that P bar can be approximated by a normal distribution whenever the sample size is large enough to satisfy these two conditions. Number one, n times P must be greater than or equal to 5, and n times 1 minus P must be greater than or equal to 5. Here are the formulas for the expected value for the proportion and the standard error of the proportion. Notice that if we have an infinite proportion, or one in which those assumptions have been met, we will use the infinite proportion formula. Only in the case that the assumptions have not been met will we use the finite population, and this particular finite population correction factor. So let's revisit our ICU data. We have an infinite population. It's a huge sample, or a huge number of cases, but they're constantly changing. Although we drew these cases from existing data, the population of individuals in the ICU next month, 6 months from now, a year from now, a year ago, those will all be different. This is a population that is constantly changing, which would make it impossible for us to draw a frame of all of the people in the population. The variable that we're interested in is the expired proportion. This is the proportion of the number of people admitted to the ICU who passed away. The population size is 4,194, and the population proportion is 0.50. What is the probability that a simple random sample of 30 patients will provide an estimate of the population proportion of patients who expired that's within plus or minus 0.05 of the actual population proportion? To do that, let's return to our sampling week 11 Excel spreadsheet and click on the tab for the ICU data. We have a column, it's column G, that's where we're going to add a random variable. And we will do this by clicking in G2 and entering equal sign, RAND, open parentheses, close parentheses. Even though there are no arguments inside of the parentheses, we still need to have the open and close parentheses for this to work. Click enter, now we have a random variable. Next, we're going to copy that formula down the rest of our column. So click on G2 and double click on the small box in the lower right corner. That will copy our formula all the way down. You will see in the boxes that I provided out here to the right, we have a box about proportions. So we need to sort our data to get a random sample of the cases. We'll do that by going to Data, sort, and that will bring up the sort box. In this sort box, we will sort by the random column, sort on values, smallest to largest, and click OK. Those first 30 cases will be aggregated in the box that says, did the patient pass away? And you will have a proportion. We know the population parameter is 0.5. How close is the proportion that you calculated to that population parameter? If we have only this one sample, we would estimate the population parameter as the value that comes from our sample of 30. And that sample is probably going to be off slightly because there will be some measurement error or sampling error. If we have multiple samples, each of the same sample size, in this case 30, we could aggregate all of those sample proportions and create a distribution of the proportion of the proportions. Well, to apply this, we're going to need to go back to that Normal Distribution MultiTool that we used a few moments ago. We're going to use in this time box 8, which is the blue box. It says sampling distribution of the proportion. Our first thing, let's add the population proportion, which we know is a 0.5, and we're using sample sizes of 30. As you enter both P and N, it'll automatically check the assumptions of whether the values are greater than or equal to 5. In this case, both of them are 15, and you get a nice note that says the assumptions have been passed. You can use the normal distribution. In other words, we will not need to use this additional set of boxes that occur out here to the right. Now we can enter proportion 1 and proportion 2. The proportion 1 is a 0.45. That is 0.5 less than our population proportion. And proportion 2 is 0.55, which is 0.5 or 0.05 greater than our population proportion. We have the probabilities for each of those proportions. We're more interested in the probability of x being between 0.45 and 0.55, which we see as a 0.4161. Okay, that's a good start. But we learned with the sample, we learned when using means that sample size influences error. As sample size increases, error decreases. Well, let's see if that same thing holds true for proportions. What is the probability that a simple random sample of 100 patients will provide an estimate of the population proportion of patients who expired that's within plus or minus 0.05 of the actual population proportion? Well, for that, all we need to do is change our sample size of 30 to a sample size of 100. Click anywhere, and we see that the probability is now a 0.6827, roughly 2/3 of the time. As we look at our sampling distribution for the proportion, we see that with a sample size of 30, the probability of choosing a sample that was within 0.05 of the population proportion is a 0.4146, or 41% of the time. Less than half of the time will that sample of 30 give us a value between 0.05 above and below. However, with a sample size of 100, that probability jumps up over 2/3, 0.6827, or 68% of the time. Feel free to enter other values of sample sizes to experiment with what happens as we add more and more cases, and what that does with our error and the number of cases that will be between the two values that we have selected. Well, what conclusions can we draw about the sampling distribution of the proportions? Like the sampling error of the mean, when it comes to sample size, bigger is better. When we have a sample size of 30 or larger, we have minimized sampling error, and so we tend to get a much better estimator. And if the sample size is large enough and the expectations are met, well, then we can use a normal distribution for our proportions.